Hello friends, welcome to Serica's Mathematics Simple. In today's lesson, we are going to be focusing on how to derive the work done formula. Okay, so by the end of this video, you will know why sometimes in some cases we calculate the work done of a force in moving a body through a distance as Lt cos theta. Now let's get straight into it. So work done always comes. Work done is the energy that is produced by a force which causes a body to move through a distance in a particular direction. Okay, so if the force, the direction of this force is 100% in the direction of movement, in the direction of motion, then the work done of that force will be given as W is equals to the force, the product of the force, and the distance through which the action or the influence of that force causes that body to move. Now, oftentimes, the force is never perfectly aligned to that direction of motion. So now let's introduce an angle theta, and then let's call angle theta the angle that the force, the direction of the force makes with. Now let me just draw this. Let me draw a figure. So let's say we have a triangle on the board. We have a figure like this on the board. We have something like this. So this comes up like that. Nope. So we use this. So this comes up like this, and then we have this. We have this again. And then now let's say this is the force. Okay. Now at this point we can lose the force. We can replace it by an arrow. So let's say this is the force. Okay. Now we'll name the force here to be F. Is that okay? And then here to be our theta. Alright. So theta is the angle this force makes with the horizontal. Now, I have a question for you. The direction of this force, what is the direction of this force? The line of action of this force is in what direction? So if you observe clearly, you will notice that this force doesn't only move in one direction. It moves both in the vertical direction and in the horizontal direction. As it slopes, as it slants like that, it is both moving upward and horizontally. Alright, so in that case, whenever we find situations like this, it means that this force F can be resolved into its horizontal and vertical component. And in this case of a work done, if we resolve a force into its vertical and horizontal component, now the component of the force that produces work done is the component that moves in the same direction as the direction of motion when the force is applied on the object. Is that okay? So if we resolve this force into its horizontal and vertical component, we are going to have, now just so you see this with clarity, we can extrapolate here like this. Now extrapolating is not good enough. Okay, so let's say we can draw a line here like this. This distance is the same as the distance of there, these two vertical lines are of the same distance, okay? The y and the x. Now, the distance from here to here is the same as from here to here. Is that okay? Now, to resolve this force into the vertical and horizontal component, you write this. So this is its vertical component and this is its horizontal component. So this is the force. So this is the force F. Now, let's go back to the diagram. Now, if we want to look for sine theta, now let's say this is the point on this x-axis, this point is called, let's call this point A, and then let's call this point here B. Okay, now sine theta is going to be the opposite side on the hypotenuse, and now the opposite side is AB. Okay, so this is a side that is directly opposite and it is a vertical side. So this vertical side AB, is equal to F, is equal to sine theta on F. Okay, what we are saying is, so sine theta, according to the diagram, sine theta is equals to AB on F. So it means AB, if you want to know this length AB, is going to be F sine theta, and this AB is the vertical component of this force. So here you write F sine theta up here. So here you write F sine theta. Okay, and then cos theta. Then what about cos theta? So let's say now cos theta is going to be, let's call this point here O. So this point is O. Cos theta is going to be the adjacent side on the hypotenuse. So cos theta, so call this point O. So cos theta is going to be, now the length OA on hypotenuse, which is F. So to get the length OA, which is the horizontal component of the force, and which is actually the component that acts in the same direction of motion, so it shows that OA, that horizontal length or distance, is equal to F cos theta, and that gives you the horizontal component of the force. And having that, you can come and write here as the horizontal component of this force will be F cos theta. F cos theta. Alright, so having this, now F sine theta is the component of the force that acts vertically upward. Okay, and F sine cos theta is the component of the force that acts horizontally. And this horizontal component of the force is a component that aligns perfectly in the direction of motion. And since F, our new force now has become F cos theta, remember we have our work equation to be W equals F times perpendicular, not perpendicular distance, F times d, where d is a distance over which the body moves as a result of the force. Now since F, our new F now is F cos theta, we can just simply write W to be F cos theta dot d, and that is how we prove now. I can just write this clearly as W is equals to F d cos theta, and this is how we can derive the formula of work done for an object which is moving in the direction of motion and makes an angle with the horizontal. If this video was helpful to you, make sure you like, you comment, and you share with other friends so they can learn. See you in our next class.